Building an embankment dam on a soil foundation confronts the designer with two basic challenges. The first is to construct the foundation to support the weight of the dam and reservoir for as long as 100 years. The second challenge is to control seepage and avoid piping. Seepage is the flow of water through the foundation, while piping is the movement of soil particles in the foundation under seepage pressures. In some existing dams, the solution to both of these challenges has been to completely remove and replace inadequate foundation materials using engineered fills. Because removing and replacing large quantities of foundation materials is very expensive, the usual solution has been to leave natural soils in place under parts of the dam. Until the early 1970s, it was common practice to leave apparently competent soils in place under the dam. These alluvial soils, which contain large amounts of sands and gravels, were deposited by the river or stream that was being dammed. Sands and gravels that are deposited by running water are relatively less dense than soils that develop in place. When they are exposed to moderate to large earthquakes, these sands and gravels may lose strength because they liquefy. Engineers began to explore and understand this condition in the 1960s, and their initial understanding was supported by the San Fernando earthquake of February 1971. That earthquake nearly failed the lower San Fernando Dam and damaged the upper San Fernando Dam. Over 80,000 people were evacuated from their homes while the reservoir was lowered to a safe level under emergency conditions by using large pumps. This event brought about the reevaluation of dam safety criteria and re-examination of the designs of existing dams exposed to earthquakes in the United States. As the liquefaction phenomena was better understood, it became apparent that natural materials left in place under many dams could not support them during an earthquake. These dams would have to be modified to protect public safety and maintain the water levels required for water storage, recreation, flood control, and hydropower generation. The modifications could generally be of two types. One would be to completely remove and replace all the liquefiable soils in the dam foundation. This usually involves excavating the dam to gain access to the foundation, a time-consuming and costly effort that often requires lowering or draining the reservoir. Typically, this approach can require that large amounts of foundation soils be excavated and replaced. A variation of this method is to excavate less soil and replace it with a structural element of some kind that is stronger than soil. The second method involves improving the strength of existing foundation soils. This method can often avoid having to excavate the dam and foundation or lower the reservoir. These incentives have resulted in several methods of improving soils in situ being successfully used to modify dams to resist earthquakes. We are fortunate to have one of the leading authorities in the field of modifying soils on site, Dr. James K. Mitchell, discuss the general field of ground improvement in this set of videos. In his first video, Professor Mitchell will present an overview of methods currently available to improve soils in situ and review selection and design criteria for those methods. In the second video, he will discuss three case histories that illustrate the application of several of these methods to dams. These are the Jebba Hydroelectric Project, Nigeria, Jackson Lake Dam near Jackson Hole, Wyoming, and Mormon Island Auxiliary Dam near Sacramento, California. His discussion will cover the significant issues and lessons learned in each case. Professor Mitchell is a recognized leader in developing and applying ground improvement techniques. He is currently on the faculty at Virginia Tech, where he was appointed the Charles E. Via Jr. Professor in the Via Department of Civil Engineering in 1994 and University Distinguished Professor in 1996. Dr. Mitchell retired from the Edward G. Cahill and John R. Cahill Chair in the Civil Engineering Department at the University of California, Berkeley in 1993. He had served on the faculty at Berkeley for 35 years, including appointment as department chair from 1979 to 1984. Professor Mitchell received his science doctorate from the Massachusetts Institute of Technology in 1956. He then spent several months at the Waterways Experiment Station in Vicksburg, Mississippi. This was followed by active duty with the U.S. Army Corps of Engineers before joining the faculty at Berkeley in 1958. A member of both the U.S. National Academy of Engineering and the National Academy of Sciences, Dr. Mitchell's achievements have been recognized by many awards. These include the following from ASCE: the Norman Medal twice, the Middlebrooks Award 3 times, the Walter L. Huber Research Prize, and the Carl Tersaghi Award. He delivered the 1984 Carl Tersaghi Lecture and the 1991 Rankine Lecture. He did extensive research on lunar soil properties and served as principal investigator for the soil mechanics experiment, which was part of an Apollo moon missions 14 through 17. NASA awarded him the Medal for Exceptional Scientific Achievement for this work. Dr. Mitchell has been active in a number of professional societies. He is a fellow and honorary member of the American Society of Civil Engineers. He has chaired the Geotechnical Board of the U.S. National Research Council, been vice president of the International Society for Soil Mechanics and Foundation Engineering, and has served on and chaired a number of other committees. He has authored over 300 publications, including 2 editions of Fundamentals of Soil Behavior, a graduate-level text and reference. Professor Mitchell consults on geotechnical problems and projects of many types, with special interest in ground improvement for seismic risk mitigation and environmental geotechnology. He has worked on many international projects and on numerous Corps of Engineer and Bureau of Reclamation dams in the United States. It is my pleasure to introduce Dr. Jim Mitchell.
Thank you, Frank. It's both a pleasure and an honor to be able to participate in this series of videos concerning dam safety. Other videos in this series illustrate a number of crucial aspects of dam safety. Dr. Ralph Peck describes and illustrates a number of remarkable case histories that date back to the early years of the 20th century. They show how seepage and piping can lead to catastrophic failure. He provides us with instruction on how such failures can be prevented through use of proper design, proper construction, and continued surveillance. Dr. Don Deere shows the necessity for thoroughly investigating foundation conditions, the geology and other characteristics of the site in terms of materials and their behaviors. He talks about the necessity to properly prepare the foundation and the abutments, as well as the contacts between the dam and the foundation, to assure both stability and seepage control. He gives us specific strategies and methods for carrying out these studies. John Lowe III uses the important experiences of Tarbella Dam in Pakistan and the Ludington Pump Storage Project in Michigan to illustrate the mechanism of sinkhole formation in seepage control blankets. He teaches how to design filters for protection against internal erosion. In his second video, he describes the destabilizing effects of sudden reservoir drawdown on embankment stability and the conditions where drawdown may be important. He tells how to do the appropriate soil testing and stability analyses to determine whether drawdown will lead to instability. Embankment dams founded above thick layers of alluvial materials are likely to utilize upstream blankets or deep cutoff walls for seepage control. Both the blanket and the embankment may be susceptible to cracking as a result of differential settlement in the foundation, drying, or settlement of the embankment and core. These problems are aggravated if the foundation materials are highly compressible. In addition, if the foundation soils are weak, there may also be risk of bearing capacity or stability failure beneath the embankment toes unless rather flat embankment slopes are used. Weak layers in the foundation may be the source of instability, as shown in the photograph of the failure at Waco Dam in Texas. Excessive creep deformations in the foundation clays at the tar sands tailings dam in Alberta, Canada, have resulted in significant horizontal displacements of the embankment. In some cases, these problems may be mitigated in new dams by using flatter slopes. The addition of toe berms to increase the strength of the subsoils and to increase the length of a potential failure surface may solve the problem in the case of existing dams. The photograph shows the berms constructed along the inboard side of the Costa Oriental dikes along Lake Maracaibo in Venezuela. These berms were constructed to mitigate the risk of stability failures under earthquake loading. The toe berm at the base of the steep slope at the Tablachaca Dam in Peru, shown in this photograph, was one of several slope stabilizing measures used for protection of the dam and the reservoir. In some cases, however, reservoir restrictions, hydraulic constraints, or space limitations may not allow for these solutions, and other treatment methods may be required. Several forms of ground modification may be used to stiffen and strengthen the ground, including densification, cementation, and reinforcement. The methods selected in any case will depend on the soil types and stratigraphy, the depth of treatment required, and whether a site is being prepared for a new dam or an existing dam is being retrofitted. Although unlikely to be a problem in properly designed and constructed new rolled fill dams, the embankments of some dams may be susceptible to failure, especially in the case of hydraulic fill structures. Many older dams were constructed of hydraulic fills, and hydraulic filling is the most widely used method for construction of tailings dams. Hydraulic fills, because of their loose and potentially liquefiable state that results from the depositional process shown in this photograph, are susceptible to sudden collapse and flow failures. The Fort Peck Dam failure on September 22, 1938, is a good example of this. Embankment construction by the hydraulic filling method had reached within about 20 feet of the design crest elevation. More than 5 million cubic yards of material moved upstream in a period of about 10 minutes. 8 workers lost their lives in the event. Flow failures may be triggered by excessive static loading, as was the case for the Fort Peck Dam failure, but more often they are caused by seismic events. Some examples of dam failures caused by earthquake shaking include the Hebgen Dam, Montana failure in the magnitude 7.5 to 7.8 earthquake in 1959, the El Cobre Dam failure in Chile in 1965, and the Lower San Fernando Dam failure in Southern California in 1971. These two photographs show the San Fernando Dam following the earthquake. More recent examples include the failure of several small dams at the Niteiko Ponds in the 1995 earthquake in Kobe, Japan. With these experiences, as well as many well-documented cases of ground liquefaction and earthquakes, has come the realization that the foundations of many existing dams are susceptible to liquefaction. Furthermore, the subsoils at new dam sites may be liquefiable, and remedial action prior to construction is necessary. In this video, I examine methods and designs for ground improvement to reduce damage and to prevent failure resulting from the above causes: settlement and excessive deformation under static load, and liquefaction flow and stability failures under dynamic or earthquake load. I will not discuss the investigations and analyses that must be made to see if there is a problem. Rather, I assume that the existence of inadequate embankment or foundation conditions has been confirmed. I will not consider the common treatments and components of dams, such as grouting, cutoff walls, and filters, that are associated with foundation preparation and seepage control. These are thoroughly described by Peck, Deere, and Lowe in other videos in this series. I will, however, touch on the use of soil cement and roller compacted concrete in hydraulic structures. These materials can provide economical and structurally sound components for both the rehabilitation of existing dams and for new dam construction. In this video, I will note some general considerations in ground improvement. I will describe several methods that are used in dams and dam foundations. I will summarize techniques for evaluation of treated ground, and I will present some considerations in the design of ground improvement. In video 2, I present 3 illustrative examples of ground improvement projects for dam safety. These include, first, the Jebba, Nigeria hydroelectric development, where deep blasting and vibro compaction were used. This is an example of ground improvement before construction of the dam. Second, the Jackson Lake Dam, Wyoming. Here, an existing dam was replaced following foundation improvement using deep soil mixing and deep dynamic compaction. And third, the Mormon Island Auxiliary Dam, which is an example of the use of deep dynamic compaction, stone columns, and drains to mitigate the liquefaction risk to an existing dam foundation. Currently available ground improvement methods that may be used to prevent excessive deformation or failures of dams under static and dynamic loads may be divided into several categories. The first category is shallow compaction using rollers. This is the most widely used method for construction of embankments. It is the best and most economical method for assuring properly densified material of known properties and behavior. It can be used to densify virtually all soil types. The major limitation of compaction by rollers is that the effective depth of treatment is limited to about 1 meter, perhaps up to 2 meters if very heavy equipment is used. I will not cover details of earthwork compaction by rollers here, except to note that replacement fills, buttress fills, and soils that are stabilized with admixtures, such as soil cement and roller compacted concrete, are usually constructed in compacted lifts using rollers. These types of fills have a very important place in construction of new dams, the rehabilitation and expansion of existing dams, and the mitigation of ground failure risk to existing dams. The second category is densification by deep compaction. Methods in this category, and illustrated by the photos and the drawings that follow, include compaction by vibrating probe, vibro compaction, also called vibroflotation, compaction piles, deep dynamic compaction, and explosive compaction. The third category of treatments includes ground improvement by combined displacement, replacement, and densification. Vibro replacement stone columns and compaction grouting are the most widely used methods in this category. The fourth category is ground strengthening by reinforcement. Deep soil mixing and jet grouting are technologies by which columns, walls, and cells of various configurations can be constructed in the ground. The strengthened and reinforced ground is then less compressible and more resistant to settlement, more resistant to shear failure, and also to liquefaction. Finally, drainage for the purposes of consolidation of foundation soils, for keeping excess water from treated zones, that is, to intercept pore pressure plumes from adjacent liquefied soil, and for reducing liquefaction potential. I will examine each of these methods in more detail later. However, there are some considerations of a general nature that are usually very important in any project, and I want to discuss them briefly first. Vibration and displacement are both useful for densification of most cohesionless soils. The idea is to break down the soil structure and rearrange the particles into a denser, more stable fabric. Experience shows that it may be easier to densify from a low relative density to a high relative density than it is to densify from a moderate relative density to a high relative density. Saturated soils containing silt and clay are much more difficult to densify by vibratory and impact processes than are clean, cohesionless soils. Vibration without displacement is likely to be ineffective in soils with fines contents greater than 15 to 20%. In such materials, some displacement, such as accompanies compaction grouting, stone column construction, and installation of compaction piles, is normally required. Experience shows also that clay fines are much more inhibiting than silt fines, by a factor of 5 or more. Furthermore, the level of improvement that may be attained, as measured, for example, by the standard penetration test N value, is considerably less for soils with high fines content than in clean, cohesionless soils. Fortunately, however, the resistance to liquefaction of soils with high fines contents is usually greater than that of clean, cohesionless soils having the same penetration resistance. Densification to a relative density of 80 to 90% is about the best that can be obtained. If very high strength and stiffness are required, then it may be necessary to use grouting, admixtures, or reinforcement by deep soil mixing or jet grouting. Most deep densification methods may not be effective within the upper few feet below the ground surface. Therefore, it is often necessary to go over the area with surface compaction after the deep densification has been completed. Soils containing large quantities of cobbles may be impossible to densify using vibratory probe type devices because of the difficulty in penetrating the ground. Very often, deep densification of soils is followed by a period of several weeks to months, during which the apparent strength and stiffness, as measured by penetration tests and shear wave velocity measurements, continues to increase above the values measured immediately following the treatment. Examples of this include the cone penetration test resistance values measured in the Jebba Dam Foundation after densification by deep blasting. The figure shows cone tip resistance as a function of depth before deep blasting and at 3 times following treatment. Significant increases during the several weeks following treatment are evident. The test results for the hydraulic fill placed for the new Chek Lap Kak Airport in Hong Kong after densification by Vibro compaction are another illustration of this phenomenon. The exact mechanisms responsible for the time-dependent improvements in properties are not fully known. Both chemical and physical processes have been hypothesized. Whatever the causes, the beneficial consequences are of sufficient magnitude in many cases that they should be taken into account by specifying a minimum time after treatment before final evaluation of the improvement obtained. Several methods are used for evaluating the results of ground improvement. These include standard penetration tests, cone penetration tests, Becker penetration tests, and shear wave velocity measurements, which are most commonly used for evaluation of deep densification. Sampling is often carried out when treatments employing admixtures are used. In virtually every project, some simple observations and estimates can be very valuable for assessing the results obtained relative to the project requirements. To avoid uncertainties and disputes, it is essential that a comprehensive characterization of the project site conditions be done before treatment. Without reliable before measurements to compare with the after measurements, it is nearly impossible to understand what has been accomplished. Methods that are used to assess the effectiveness of treatment include the following. Surface settlement or heave measurements are simple and should always be made. Soil backfill quantities added to holes and craters should always be measured. Samples of materials treated using admixtures should always be taken and tested. The standard penetration test is widely used. The cone penetration test provides a continuous record with depth. The Becker penetration test is useful for soils containing gravel and cobbles. Shear wave velocity measurements can be made downhole and crosshole or non-invasively from the ground surface. The pressure meter test has been used on some projects, and the flat plate dilatometer test has seen limited application at other ground improvement projects. Undisturbed sampling of treated ground may be warranted in some cases. In situ shear tests may be useful in finer grained soils. And finally, in situ measurements of hydraulic conductivity may be needed to determine the effectiveness of seepage barriers. The SPT and the CPT are most widely used, with the CPT becoming the test of choice, provided the soil conditions are suitable. Both of these tests are useful for assessment of the post-treatment liquefaction potential using the simplified method. Shear wave velocity measurements are also useful because they can be made non-destructively from the ground surface. Comparisons of unimproved and improved ground profiles for a site are shown in the accompanying figure. Profiles determined using the standard penetration test, the cone penetration tests, and the pressure meter tests are shown. It may be seen in each case that the increase in measured quantity was significant, indicating that the densification method was successful in increasing the soil density and strength. Before and after comparisons in the form of SPT N values plotted on a liquefaction resistance plot of cyclic shear resistance ratio as a function of the normalized standard penetration resistance, or N160, are shown here. The region to the left of the curve represents liquefaction likely, whereas the region to the right of the curve represents liquefaction unlikely. Data for the several sites shown are separated into values for untreated and treated ground. The actual soil behavior in the Loma Prieta and Kobe earthquakes was consistent with these values. When penetration tests are used or samples are taken, usual practice is to measure or sample at the locations where the improvement is likely to have been the smallest. Usually, this will be at the center of a triangular or square array of densification probe insertion points. This is a conservative approach, but it is justified because of uncertainty about how large weak zones can be before the overall performance of a site is adversely impacted. All of these considerations must be kept in mind for each project. Now we're ready to examine different methods for ground improvement in further detail. The choice among the available methods for ground improvement depends on soil type, required depth and area of treatment, site constraints, level of improvement required, and costs. Local experience and the availability of materials and equipment are also important considerations. The diagram shows a general relationship between different methods and the range of soil types that can be effectively treated by each. It may be seen that not all methods are suitable for all soils. This situation is very similar to that in the field of medicine, wherein different medications are used to treat different diseases. Vibro compaction densification of cohesionless soils is accomplished using vibrating rods, pipes, and probes. The photo shows a simple system, which consists of a closed-end steel pipe pile, about 30 inches in diameter, suspended by a vibratory pile hammer. In systems such as this, where the energy input is at the top, the effective depth of treatment is limited, owing to energy losses into the ground along the probe. Most commonly in the U.S., a vibrofloat is used, in which a horizontally oscillating vibrator located near the bottom provides energy input directly at the depth where the soil is being densified. The vibrofloat is jetted or vibrated to the desired depth, and then the ground is compacted from the bottom up, backfilling as you go. Backfill consumption is typically about 1 cubic meter per meter of column. The vibrator frequency is usually 1800 or 3000 RPM. The ground is compacted radially away from the probe. The backfill that is dumped in around the probe may be either the native sand or imported clean granular material. Vibrocompaction is best suited for granular, free-draining soils, that is, soils with a hydraulic conductivity greater than about 10 to the minus 6 meters per second. A 10% particle size greater than 0.03 millimeters is desirable. The effective treatment of clean sand may result in increases in standard penetration test penetration resistance N160 values to 25 blows per foot or more, and cone penetration resistance values of 15 megapascals or more. Vibro compaction has been used effectively to depths up to 100 feet. Vibro replacement stone columns are constructed in a manner similar to the vibro compaction process, except that a clean gravel or crushed stone backfill is used. Vibro replacement is suitable for soils containing a higher fines content than can be effectively densified using vibro flotation alone. In the wet stone column process, water jets assist in advancing the probe to the desired depth, and they wash finer material to the ground surface. In the dry process, the backfill is dropped down a pipe alongside the vibrofloat, and the in situ soil is pushed radially outward from the probe. Properly constructed stone columns are typically about 3 feet in diameter, with the diameter being larger in weak soils than in stronger soils. Stone columns have been used to depths greater than 60 feet. In addition to the densification of the in situ soil by vibration and displacement, the stone columns act as reinforcing elements because of their higher strength and greater stiffness relative to the soil. As the columns have much higher hydraulic conductivity than the native ground, they also can provide drainage. Thus, stone columns can be used in a variety of ways, as we see in the diagrams, including support of vertical loads for increased bearing capacity and decreased settlement, increased soil resistance along potential sliding surfaces for improvement of stability, mitigation of liquefaction potential, and as an aid in drainage. Methods for the analysis of the composite column soil system are available. Ground improvement using compaction piles is accomplished by driving displacement piles or by driving a replacement backfill out of a casing as it is withdrawn from the desired depth of treatment. Compaction piles are typically spaced 3 to 10 feet on center, and they have diameters of the order of 3 feet after compaction. Compaction piles densify the soil by displacing a volume of soil equal to the pile volume and by vibration during driving. The installation of compaction piles may be relatively slow and expensive. Improvements obtained using compaction piles are usually very good, however. Deep dynamic compaction is much like Proctor impact compaction done in the laboratory, only on a much grander scale. It is an economical method for densification of saturated cohesionless soils, collapsing soils, or partly saturated soils to depths of up to 30 to 40 feet. It is restricted to the improvement of relatively large open areas where the closest impact points are 100 to 125 feet away from existing structures and facilities. Typically, weights of up to 30 tons are used, dropped from heights up to 100 feet. From experience, it is common to use a weight in tons approximately equal to the height of drop in meters. The craters created by the drop weights are usually backfilled periodically, and a final ironing pass may be used to densify the soil near the ground surface. Greatest densification is a few feet below the surface, with effectiveness decreasing with further depth. A schematic of the variation of post-treatment density with depth is shown in the diagram. In general, the effective treatment depth in meters equals 0.3 to 0.7 times the square root of the product of the drop weight in tons and the drop height in meters. The finer grained the soil, the lower the value of the coefficient. Weights are dropped in a grid pattern across the site, with several drops at each impact point. For the initial coverage, the impact points are laid out in a grid pattern with spacings of the same order as the desired treatment depth. For subsequent coverages, intermediate impact points are used. Typically, 2 or 3 coverages are used. Design guidelines are available to aid in the selection of the total energy input required and for estimation of the improvement that is likely. Explosive compaction, or densification by deep blasting, can be an economical method for improvement of saturated, clean, cohesionless soils. It can be used in soils containing cobbles and boulders that could inhibit densification using vibro probes. It can be used to treatment depths well over 100 feet. depths greater than can be densified by the other methods that have been described. The general procedure for blasting compaction beneath the ground surface is first, lay out a pattern of charges. Second, install a casing to the desired depth of a charge location. Third, place the charge in the casing. Fourth, backfill the casing. And fifth, detonate the charge. Blast densification is much like a series of small earthquakes. It causes loose, saturated, cohesionless soils to liquefy. Compression waves, or P waves, from blasting generate pore pressures that break the soil structure apart. Shear waves, or S waves, cause soil grain displacements and densify the soil structure. Excess pore pressure may be vented at the ground surface in the form of sand boils. There is often a large time effect, that is, an increase in strength and stiffness with time, but without further increase in density, perhaps due to the time-dependent dissipation of gas pressures and chemical effects. Blasting is best for soils with an initial relative density less than about 50 to 60%. Full saturation and good drainage are needed. Silts and clays impair the effectiveness of the method because they damp the explosive energy and they inhibit drainage. Experience-based guidelines are available to aid in the selection of charge sizes, spacings, depths, and numbers of coverages. For most projects, a test program is carried out prior to the final design and production blasting. Charge weights of 2 to 15 kilograms at spacings of 3 to 8 meters are typical. An effective blast densification program may produce a surface settlement of 2 to 10% of the treated layer thickness. The photo shows a blast hole after detonation at the Sainte Marguerite Dam site in Quebec. The post-blasting sand boil is evident. At this site, blasting was done during the winter so that the frozen river could be used as a working platform. In the deep soil mixing process, large diameter augers, acting alone or in groups of up to 3 or 4, drill to the desired treatment depth. Cement or other stabilizing material is injected as the auger works its way up out of the hole. The soil cement mix that is left behind hardens to form a strengthened column or wall. Individual auger and column diameters up to 6 feet or more are possible. However, auger diameters of about 2 to 3 feet are more usual. The technology of deep soil mixing has developed rapidly in recent years, and deep soil mixing applications can be expected to increase in the future. The strength of the mixed soil in DSM columns is likely to be in the range of about 100 to several hundred pounds per square inch, depending on the soil type and state, and the admixture type and amount. Analyses and field performance records show that a relatively weak soil reinforced with deep soil mixed columns will act as a composite material for the purposes of supporting vertical loads, or providing excavation support, or acting as a gravity wall. The native soil replacement ratio for such applications is typically 25 to 35%. The replacement ratio is the ratio of the plan area of the cement columns to the total plan area of the treated ground. In compaction grouting, a very high viscosity soil water or soil cement water mix corresponding to zero slump concrete is injected at pre-selected depths to form dense bulbs that are 3 feet or more in diameter. The surrounding soil is displaced spherically away from the injection point as shown. This displacement causes densification of the injected soil, and the grout bulb hardens to form a highly resistant zone. Although this is a relatively slow and expensive process, compaction grouting can be carried out in small and confined areas. The treatment zone can be limited to the weak or liquefiable layers. There are no depth limitations, and it can be used in almost any soil type. Compaction grouting can be used to fill voids, to densify collapsible soils, and to consolidate partly saturated soils. High injection pressures are required to force the viscous grout from injection pipes that typically have diameters of about 2 inches. Pumping rates are in the range of a half to 10 cubic feet of grout mix per minute, and injection points are in the range of 3 to 15 feet apart, depending on the soil conditions and project needs. Typical grout replacement of the soil is 3 to 12% by volume. In calculating the replacement ratio and in assessing the overall densification associated with compaction grouting, it is necessary to account for lateral displacement of the adjacent ground and any surface heave that may occur. With jet grouting, very high, that is several thousand psi, injection pressures are used to jet water and water admixture mixes into the ground. The schematic diagram and the photograph show the jet grouting process. Jet grouted columns are typically about 3 feet in diameter in U.S. practice. However, larger columns are possible. Single rod for grout jets only, double rod for separate grout and air jets, and triple rod for separate injection of grout, water, and air jet grouting systems are used. Some applications of jet grouting include scour protection, underpinning, excavation support, and ground strengthening and impermeabilization around tunnels and shafts. Although an expensive method for ground treatment, jet grouting has several unique advantages, including nearly all soil types can be treated. There is some control over design strength and hydraulic conductivity. The treatment locations can be localized. Treatment at large depth is possible. For example, the foundation material at Terzaghi Dam in British Columbia, Canada, was jet grouted to a depth of about 500 feet. It is possible to work in confined and restricted areas. There are no large ground vibrations. As noted earlier, roller compacted concrete, or RCC, has become a widely used material in dams and other hydraulic structures. This is because of its high strength, its relatively simple formulation, its ease of construction, and its low cost. RCC is used for such purposes as buttressing existing slopes and dams, protection of dams from overtopping, linings for canals and channels, and filling cavities. It has been used as the embankment material for construction of many dams in recent years. The diagram shows a comparison between the cross-sections of typical earth fill, rock fill, and RCC dams. Given that similar construction procedures are used for each material, it is clear that the higher material cost of RCC can easily be offset by the greatly reduced quantity of material that is required. The photo shows the 195-foot-high Gibraltar Dam in Southern California that was recently retrofitted using a roller compacted concrete buttress section to improve seismic safety. A typical roller compacted concrete contains coarse to fine aggregate with a fines content of 0 to 15%. Maximum aggregate size is 1 to 3 inches. The cement content is 100 to 500 pounds per cubic yard, and many times fly ash is also added. The water content is adjusted to produce a mix that is readily compacted using conventional earthwork rollers. The compressive strength of the resulting material is usually in the range of 800 to 4,500 pounds per square inch. Finally, filters and drains are essential and integral parts of all dams. Their proper design and installation are vital for dam safety. Special drainage measures may also be included as parts of a dam foundation improvement before construction or for mitigation of embankment and foundation problems in existing dams. Prefabricated vertical drains, which are commonly called wick drains, can be installed to accelerate consolidation for purposes of reducing subsequent settlement and for increasing strength. In a recent case, wick drains more than 200 feet long were installed through a large tailings dam. The purpose was to accelerate the consolidation of both the fine-grained embankment material and the foundation clays to alleviate an instability condition. Some studies have been made recently to determine if wick drains can also be used in silty and clayey sands to enhance densification by vibratory methods. Drainage blankets are commonly placed over ground that has been treated using stone columns to prevent buildup of excess pore pressure and facilitate the rapid removal of any water that drains into the columns. Gravel columns or gravel-filled trenches are sometimes placed around the perimeter of zones that have been densified to prevent liquefaction. The purpose of these drains is to intercept excess pore pressure plumes before migration into the treated zone can result in strength loss. I have now provided a brief overview and illustrations of methods that may be used in ground improvement applications for dam safety. Much greater detail, along with numerous case history applications, is given in readily available references. Specialty contractors experienced in the use of the different methods are very valuable sources of information, especially about materials, construction procedures, and costs. With respect to the latter, the total costs for any specific project depend on many factors, and it is difficult to generalize. Nonetheless, the different treatment methods may cost very different amounts. For example, the cost of densification by explosive compaction is likely to be much less than that by Vibro compaction on a per unit volume of ground improved basis. Similarly, compaction grouting and jet grouting are more expensive than stone columns. Some very approximate costs in 1998 for different methods of ground improvement are given in the table. These figures are intended as rough guides for equipment mobilization and treatment under normal conditions. Each ground improvement project is unique in many ways. Therefore, a prescriptive procedure for analysis and design that covers all the important aspects and fits all situations is not now and probably never will be possible. Nonetheless, a general procedure that incorporates several steps is often helpful in arriving at good solutions. The determination of the need for ground improvement and the development of ground improvement design might proceed in the following way. First, define the project and project performance requirements. What is the ground improvement for? What are the settlement, deformation, and seepage limits? What factors of safety are mandated? Second, what special demands will be put on the facility? Will it be subjected to floods or earthquakes? The hazards must be analyzed and the loading that will affect the dam must be quantified. Third, characterize the site. What are the strata? What are the properties of the materials that are encountered? What is the groundwater regime? Fourth, evaluate stability, seepage, and liquefaction potential so it can be determined if ground improvement is needed. If, as a result of these determinations, the need for ground improvement is established as the best approach for mitigation of the problems, then a series of design steps can be followed. First, establish the level of improvement required to ensure satisfactory safety and performance. Second, develop and evaluate remedial design ideas. Concept meetings for brainstorming possible treatment strategies can be very effective at this stage for identifying all the schemes with potential applicability. Third, consider the pros and cons of each concept and select 2 or 3 for further evaluation. Fourth, establish the location, the size, the shape, and the required properties of the treated zones. Fifth, do field tests to determine if the methods will really work, to confirm the design assumptions, and to develop construction procedures. Sixth, prepare specifications and develop QC/QA programs. In this video, I have described the types of dam safety projects and problems that might be addressed using ground improvement. Some general aspects of different methods, how they work, and how they are evaluated were considered. Then each of several specific deep densification, grouting, mixing, and drainage methods were described in more detail. Finally, considerations in the selections of method and design of the treatment were described. In the next video, I will show how several of the methods that have been described in this video were used on 3 important dam projects. Each case history involves special problems that needed to be addressed by the choice and implementation of these methods.